Today we're going to talk about conjugate pairs. And basically what a conjugate means is that we change a sign. So the conjugate pairs, given that f is a polynomial whose coefficients are real numbers, the conjugate pairs theorem states if we have a root of a plus bi, then we change a sign in that binomial, and we have also an a minus bi. Now the thing about conjugate pairs is that it only works when the values are odds. So we have to digress for a minute here. Remember that the square root of -1 is I. But what we don't necessarily know is what does I squared equal? And I squared equals -1. So, given the degree of the polynomial and information on some of the roots, state the missing roots. Well, a reminder here. Degree 4 in our first example. Degree 4 means that we're going to have 4 roots. And right now, what we know 4i is a root, 3 is a root, and -i is a root. And we can use our conjugate pairs theorem when we see the I. Since 4i is positive, we're going to make a -4i. And then we've got our 4th root. 4i, -4i, 3, and -8. There's our 4 roots. If we look at example number 2, degree 3, and we have 2 roots listed. We've got I square root of 11 and 6. Whenever we see an I, we're going to apply our conjugate pairs theorem. I square root of 11 is positive, so we can say -I square root of 11. 3rd degree, 3 roots. Positive I radical 11, -I radical 11, and 6. Over here on number 3, degree 4. This time we are only listing 5 plus I as one of the roots, and -I square root of 3. 4th degree means we need 4 roots. So we have to have 2 conjugates this time, and conjugates mean that we're going to change the sign. So we have 5 plus I. This is going to become 5 minus I. We have -I square root of 3, so we're going to have positive I square root of 3. Watch out for the degree. The degree tells us how many roots we're going to have. But ultimately, what we're really going to be working with here today is writing equations of polynomials. So when we take a look at our first example here, and let me read here. Write a polynomial of the least degree, which just means create a polynomial with the lowest degree possible, with integer coefficients, so no fractions, that has the given zeros, which are also known as roots. Graph in your calculator to check the roots. I'm not going to spend the time graphing in the calculator, but if you would like to, you can see real roots on your calculator. You can't see the 2i. And by the way, what is the conjugate of 2i? It's going to be -2i. So this is similar to what we did with our building polynomials earlier in this unit. Now that we've got our roots here, we can say x equals 5, x equals positive 2i, and x equals -2i. And maybe you don't need to write the step. And of course, on the first example, it's probably helpful. But what we're going to do is we're going to subtract 5 from both sides. So we get x minus 5. We're going to subtract 2i from both sides. We get x minus 2i. We're going to add 2i to both sides. We get x plus 2i. So what we did is we took the roots, and now we created factors, and we're going to multiply all of our factors together. We have x minus 5, and x minus 2i, and x plus 2i. We need to multiply these three together. And typically what we do is we multiply the first two together, get an answer, and then we multiply by the third. But I can make it just a little bit simpler here today. Because if you notice on these second two parentheses, the only difference between them is one of them has a minus sign in it and the other one has a positive sign in it. Difference between two squares. It might be a little bit easier to multiply these two together first, and you don't have to. And then once we get our answer there, multiply it by x minus 5. Let me say one more time though. You can multiply the first two together, get an answer, and then multiply by the third. That works perfectly well. I'm going to stick with this. First, outer, inner, last, if you prefer, double distributive property. But now we have x squared plus 2ix minus 2ix minus 4i squared. First, outer, inner, last. And the advantage here of multiplying these, like I said, difference between two squares, we have positive 2ix and negative 2ix. They cancel out. And down here we've got x squared minus 4 times I squared. If we look above on our paper, what does I squared equal? It equals negative 1. So let's fill that in. So what we have now is we have our x minus 5, which was the first polynomial that I haven't touched yet. And when we simplify our green polynomial here, we get x squared plus 4. Negative 4 times negative 1 is positive 4. And we're going to have to FOIL again. Double distribute again. X times x squared is x cubed. X times 4 is 4x. Negative 5 times x squared. And negative 5 times 4 is negative 20. No like terms on that. But what we do want to do here is we want to write our polynomial in standard form. Well, x cubed does go first, but then it's going to be minus 5x squared plus 4x minus 20. It makes sense here that our degree is 3 because we had 3 roots. We had 5 and 2i and negative 2i. So our degree is 3. What do we call a third degree polynomial? And I know we don't ask it here, but what do we call it? Cubic. It's a cubic polynomial. Just to keep those words fresh in our minds, the maximum number of turning points is 1 less than the degree. So we have 2 turning points. And then finally, once again, worst comes to worst, type your answer into the calculator to look at the end behavior. But if you notice on this particular polynomial, our leading coefficient is a positive value. It's a 1 in front of the x cubed, which is positive. And whatever our leading coefficient is tells us how we finish. So at the very bottom of our box here, x approaches positive infinity. We're going to be going to positive infinity. This is an odd polynomial because it's degree 3, which means that our end behavior is going to go in opposite directions. Odd starts with O, opposite starts with O. That means that this is going to be going to negative infinity, since our end behavior to the far right of a graph goes to positive infinity. Again, if that's confusing for you, look at the picture on your calculator. Number 5. First thing that we need to decide is, do we have a missing root? And we've got an I in our problem, so we have a missing root. When we have a missing root here, it has to deal with the i's, and all that has to happen is that we have to change a sign. We have 6 plus 3i. When we change one sign, it's going to be 6 minus 3i. So when we write this, what we'd start off with is x equals 6 plus 3i. And then we'd also go and say x equals 6 minus 3i. But there's a little trick that we can use to this one that I'd like to show you that will make it a little bit simpler than subtracting everything over to one side and then multiplying them out. And what the trick is once again, if you notice, there's only one difference. The signs are different. Everything else is the same. So we could rewrite this as x equals 6 plus or minus 3i. And what we want to do next is we want to isolate the plus or minus part of the problem. So we're going to move the 6 over to the other side. We get x minus 6 equals plus or minus 3i. Well, what we need to do is we're trying to come up with a polynomial. We've got 2 roots, so it's gonna be a quadratic. So we need to square both sides. And we know that squared means times itself. So this becomes x minus 6 times x minus 6. But it does look pretty weird over here with this plus or minus 3i. Notice what it is as I write this off to the side. You might want to write it right beside your problem up here, because that's where you've got some space, conceivably. But this means positive 3i times positive 3i. And positive 3i times positive 3i means 9i squared. 3 times 3 is 9. I times I is I squared. Well, but we also have plus or minus. We've got minus 3i times minus 3i. Negative 3 times negative 3 is positive 9. I times I is I squared. It does not matter when we square 3i, whether the value is positive or whether the value is negative, because either way, when we square it, we end up with a positive. So back here in our problem, when we square plus or minus 3i squared, it becomes 9i squared. On the left side of our equation, we're going to have to FOIL, like we did on the last problem. So we're going to get x squared minus 6x minus 6x plus 36. First, outer, inner, last if you're using the FOIL method. On the right side, what does I squared equal? -1. And I can recommend, even to people watching the video, the more you answer that question out loud, the better you will remember it. So if we simplify a little bit, we have like terms with the 6's, so we get x squared minus 12x plus 36 equals -9. And finally, we can put our polynomial in standard form when we add the 9 to the other side. we end up with x squared minus 12x plus 45, which is what's going to go in our box here in a few minutes, or less, when we fill this in. Standard form. If you want to get technical, it's f of x equals x squared minus 12x plus 45. Our degree. Well, it's 2. We had 2 roots. It makes sense that it's second degree. What do we call a second degree polynomial? And it's a quadratic. Again, I know that we didn't ask that, just trying to keep those words in our head. Maximum number of turning points is 1. 1 less than the degree of the function. This is an even function. The 2 tells us that it's even. So if our end behavior is going to go in the same direction, they're either both going to go to positive infinity or they're both going to go to negative infinity. Our leading coefficient on this problem is positive. The number in front of the x squared is a 1. 1 is positive, which means that we're going to finish going to positive infinity. And because it's even, we're going in the same direction. So that as x approaches negative infinity, we're also going to be going towards positive infinity. Let's flip our paper over. We've got roots of negative I squared root of 7, 4, and 0. Do we have any missing roots? And we see an I in there. When we see an I in the roots list, we have a missing root. And this is going to be changing one sign. I times the square root of 7. And when we look at this now, when we write this down, what we've got, and by the way, you might want to write what I'm writing down above the problem just so that you have a little bit of space. This one is a little bit lengthy, but we have x equals negative I squared root of 7, x equals positive I radical 7. We also have x equals 4, and we have x equals 0. And some of you don't even need to write that step down. You go directly to translating this into the factors, which is good. But if you have to write it in this format, what's going to happen here is we're going to add I radical 7 to both sides. So we have x plus I radical 7. We can subtract I radical 7. And we have x minus I radical 7. And if you did well like I just did well, I've got these two lined up. We've got factors right here. We don't even have to write it again. And the same thing's going to happen with the blue roots. We're going to subtract 4 from both sides, and we get x minus 4. And we're going to subtract 0 from both sides. We'll get x minus 0, which I write very small, because I'm highly recommending that you don't write the 0 down. X minus 0 is just x. So now what we're going to do is we're going to multiply the pink together, we're going to multiply the blue together, then we're going to multiply those together. So we're going to multiply the pink together. We're going to use our FOIL. X times x is x squared. X times negative I radical 7 is minus x I squared root of 7. Then we do our inner. I radical 7 times x is positive xi radical 7. And then here, positive times negative is negative. I times I is I squared. Square root of 7 times square root of 7 is square root of 49. Some of you already simplified, and I'm fine with that. But we are going to have to simplify. The nice part at this point is we've got a negative xi times the square root of 7 and a positive xi times the square root of 7. Those cancel out. The winner pink will end up with x squared minus I squared. Well, what does I squared equal? It equals negative 1. Square root of 7? Sorry, square root of 49. I gave it away. Square root of 49 is 7. And finally, for our pink part of the problem, we're left with x squared plus 7. But we still have the blue. So we'll come back over here and distribute the x. X times x is x squared. X times 4 is 4x. So we're going to take that value of x squared minus 4x and multiply that with our x squared plus 7. So lots of foiling or double distributive property today. And what do you do? X squared times x is x cubed. X squared times negative 4x is negative. What did I do wrong? Should be x squared. Sorry about that. We have to go back and fix that. I copied it down wrong. X squared times x squared is x to the 4th. X squared times negative 4x is negative 4x cubed. 7 times x squared is 7x squared. And 7 times negative 4x is negative 28x. And the nice part is that polynomial is in standard form for us. It's in descending order. Our highest exponent is first and so forth. So our function here is x to the 4th minus 4x cubed plus 7x squared minus 28x. And what's our degree? 4. We had 4 roots. And sure enough, we better end up with 4th degree. Maximum number of turning points is 3. What do we call a 4th degree polynomial? It's called a quartic. And unfortunately, we made the leading coefficient positive on all of the functions in this one, but that helps with our turning point here. The leading coefficient, again, is positive because the number in front of the x to the 4th is 1. That means to the right of our graph, we're going to be going towards positive infinity. And that's the second part. It's the very bottom in our box. As x approaches infinity, y approaches infinity. Because this is an even function, they go in the same direction. So as x approaches negative infinity, y still approaches infinity. If you are struggling with that, type that in, type the picture. Type the standard form into your calculator and look at the picture to determine what your end behavior is. To finish our last example here, we need to first of all ask ourselves, do we have any missing roots? And it turns out that we do not, because we don't have an I in the list of roots. So we don't have any missing roots on this particular problem. And what we can look at here is we have x equals 2, and we have x equals the square root of 3, and we have x equals negative the square root of 3. But because we have positive the square root of 3 and negative the square root of 3 listed as roots, they have to be listed, we can use that same technique that we used on problem number 5. Now we still have to do this part here. We have to subtract 2 from both sides. So one of our polynomials is going to be, or one of our factors is going to be x minus 2. But just to reinforce what we did on example number 5, because again these two are just one sign different, we could rewrite this as x is plus or minus the square root of 3. Now the goal here is that you isolate the plus or minus part, which we had to do some work for on 5, but we don't have to do the work for it. It's already isolated. So what we're going to do is we're going to square both sides. Once again, the reminder here. Positive the square root of 3 times positive the square root of 3 and negative the square root of 3 times negative the square root of 3. Both equal the same value. Positive times positive is positive. Negative times negative is still positive. So when we square both sides here, we get x squared equals positive square root of 9. Well, what's the square root of 9? Square root of 9 is 3. Now we want to put it into a factored form here so we can finish our problem. We're going to subtract 3 from both sides. And we end up with x squared minus 3. And we're going to take that value and we're going to multiply it by our other factor that we came up with a couple minutes ago at the top left of the screen, px minus 2. So maybe a slight bit quicker than the way like we did problem number 6 and 4. But we're going to FOIL. X times x squared is x cubed. X times negative 3 is negative 3x. Negative 2 times x squared. And negative 2 times negative 3 is positive 6. No like terms in this, but we do need to put this into standard form. Standard form means descending order here. It's going to be x cubed minus 2x squared minus 3x plus 6. Our degree, highest degree, 3. We had 3 roots. We didn't even have any missing roots. We just had 3 roots. Maximum number of turning points is 1 less. It's going to give us the 2. Like I said before, all of our examples today ended up to have positive leading coefficients. Because this is positive, we're going to finish positive, going towards positive infinity. So as x approaches positive infinity, y approaches positive infinity. Because this is a cubic function to the 3rd degree, it's an odd function, our end behaviors go in opposite directions. So our original, as x goes to negative infinity, we're also going to go to negative infinity.